Welcome to Brain Vision.
For this question, we have an incoming alpha particle with a kinetic energy Ki equal to 4 MeV, which I convert to joules. So this is 6.4 times 10 to the minus 13 joules. To figure out the distance of closest approach, we're going to assume that the initial kinetic energy coming in from the alpha particle is going to be equal to the final kinetic energy that's leaving from the alpha particle. Well, the final kinetic energy from the alpha particle is going to be due all to the not final kinetic energy, final potential energy. The final potential energy is going to be all due to the potential energy from the electromagnetic interaction. So this is equal to K, constant, times the charge of the alpha particle, Q sub alpha, times the charge of gold, we'll call this Q sub AU, divided by the distance of closest approach, R. So we can simply solve for R. We find that R is equal to the constant K, which has the value of 8.99 times 10 to the 9 Newton times meter squared per C squared. We multiply this by the charge of the alpha particle. The alpha particle has two protons, so this is 2 times E, where E is the charge of an electron or the charge of a proton here, multiplied by 79, because there's 79 protons in gold, 79 times E, all divided by K sub I. So we plug in our values here and we find that R is equal to 5.69 times 10 to the minus 14. And the units here are meters. We can box this in as our solution for part A. So let's go ahead and indicate off to the side that this was part A. So moving on, now we're doing part B, where we are asked to find the force from the Coulomb force here. So now that we know the distance of closest approach, we can use that, and we find that F here is equal to, using Coulomb's law, the constant K times the charge of the alpha particle, which is 2e, times the charge of the gold particle, which is 79e, gold atom, divided by r squared. So plugging those values in, we find that the force is equal to 11.3 newtons. We can box that in as the solution for part B.